This video is intended to show the use of the spreadsheet functions in a fictitious but somewhat realistic situation of TectraNologian. She just graduated from college where she studied technology management and has landed a job with an initial salary of $60,000 annually. Tectra decided she would immediately start an investment program by investing 10% of her salary or $6,000 each year starting at the end of her first year on the job. She's been quoted a rate of 5% interest annually on her investment. Let's see what this comes out to at the end of 30 years. So it's $6,000 annual payment. Initial investment is zero because she's broke coming out of college, like most college students are, in 30 years. So it starts with a future value of zero and at the end of year zero when she starts. Into year one, she deposits $6,000. There's no interest during year one since there was nothing deposited during years one. At the end of year one is 6,000, so the balance is 6,000. D8, which is the future value here, plus the 6,000, plus the interest, ends out to be 6,000. The second year, interest would be 5%. That's here's the equation, C3 times D9. The interest is $300. The deposit is C2, same dollar sign, so it's not going to change. So we have 6,000 plus 6,000 is 12,000 plus 300 is 12,300. Since we use dollar signs here, dollar signs on the rate here, and this equation's here, we can just take this, all three, locate in the lower right hand corner and drag it down. Let's make this more obvious. Whoops, I messed up. Go back here. I'm going to delete this just so you can see what's happening. We take those, shade those three, locate down here, drag it down to year 30, and there's all our calculations and a tabulation, which comes out and we show at the end of 30 years have $398,633. Not too bad, but we can do that more easily with a future value function, which is C3, C5, minus C2, C4. I'll put this here and then go back up. Do it over here and it shows those shaded. C3 is the rate, 5%. C5, number of periods, which is this one. C2, annual payment comes out of our pocket, so it's negative. We put a minus sign in front of it. C4, it's zero. We wouldn't need the minus sign, but it's initial investment, which would come out of our pocket if it was one. And when you do that, you end up with the same number as this, which you should be. That's a good check to do it both ways. $398,633 for doing it this way. You get the same thing. Now let's suppose that we want to add initial investment of $1,000. Maybe she was given a graduation present of $1,000. So she inputs that, opens the fund with $1,000 into year zero. What will this do to the final value? Well, we could do a tabulation, which is 1,000 to year one. We add 6,000 plus $50 interest on that 1,000. We get 7,050. Take that all the way down. It now is 402,000. So doing this in a future value function, the payment is the C44, but it's a 6,000. But we've added the present value is C46. If I could get this to do what I wanted to, then go over here, go up. Here's those values. C46 is a 1,000 and so forth, all of them right there. So with the future value function, you get the same answer with a lot less work. The increase then from 1, we take the D82 minus D40. Here's a D82. Subtract out the D40, which is the one up here. And by putting $1,000 up front, it increased the end benefit by over 4,000, 40,322 to be exact. Now let's look at some other variations on Tectra's retirement plans. Suppose she wanted to do it for 40 years. She did 40 years. She put 40 in the equation. Instead of 30 we had before, it goes up to 724,000. So from 402, that's with the 1,000 up front. This one, did we have that in there? No, we did not. So we got to compare it to this one up here, which is 398,000 to 724. The 10 extra years made almost doubled it. You earn a lot of interest in those last few years, 16, 17, 18,000, 28, 9, and 30. That's going to keep going up for years 31 to 40. So it makes a big difference. Compounding really comes in and makes a large difference in later years. If we go back to 30 years, but say she has a chance maybe to invest at 10% interest somewhere, a risky investment, but she figures she's young. If it goes bad, she has time to recover. If you put in 10% in the equation, it looks like this. She could earn $986,000. It was $400,000 before, now it's $986,000. 10% does as much more even actually than the extra 10 years. This changes 5 to 10%. What if she said, well, gee, how much would I have to pay I'd like to have $1 million in 30 years. That's what my really goal is. I could really retire and live pretty good on $1 million. Well, let's see how much she would have to pay each year. 5% interest for 30 years, no down payment up front, just $1 million. That's what all those zeros are. This, she would have to put in $15,051 a year instead of the $6,000. That's a pretty good chunk out of your $60,000 salary. But if she's single right out of college, that's possible to do if you really can discipline yourself. Excuse me. What about a rate to achieve $1 million exactly? $6,000 is the payment for 30 years, no upfront, no present value, down payment. To get $1 million, she'd have to earn 10.07 interest. Instead of the 10% we had here, just a little bit higher, 10.07, she'd have her $1 million. Now, she's not sure about that either. Let's try this rate. What rate if she went to a $5,000 payment? What would she have the rate to have to get $1 million? So here's the $5,000 payment. 30 years, the rate would go up to 11% interest. Another option is that she has an inheritance from a few years back that's invested, but maybe she put that into this program as initial investment. What initial investment would Tectra have to make to have $1 million back at the 5% interest? We'll do it for 40 years in this case, just to show the changes you can have. 5%, 40 minus 6,000, that's the payment. The future value is 1 million. The present value, using the present value function, would be 139,143. If she could take out of her inheritance or had that much inheritance, 139,000, put that in the account to open it with, and then 6,000 a year for 40 years, she'd have her $1 million even at the 5% rate. And that shows how to use the various functions in various situations. Big thing is to keep the signs correct and make sure you have the right functions in the right place. And you'll be in good shape. Thank you.